Yeah, thank you very much. Let me, as I'm the final speaker, so to speak, who speaks both at Bonn and here at Cambridge, let me take the opportunity and thank the organizers for organizing such a wonderful, inspiring, and productive workshop. And I think it has been a fantastic event, and we look forward to future ones. So thank you very much. Besides this, I want to make later another remark, namely why this conference has been organized exactly at an almost optimal time, but I come to this later. So what I'm talking about is a connection between homotopy theory and C-star algebraic quantum spin systems. So I want to connect homotopy theory with C-star algebras. And so we work in the setting of gamma a lattice, which is usually z to the power d, and h will be usually a finite dimensional Hilbert space. So Hilbert space. And then for any finite lambda in the lattice, put a lambda of h will be the tensor product of these finite dimensional matrix algebras. And then we can look at the co-limit in the category of C-star algebras, a gamma of h, the co-limit of lambda and gamma of those. So in Bruno Nachtergael's talk, this was explained in a little bit more general situation, but in detail. So you can take the unions of all those a lambda h's and then complete them. Okay, and now the next thing is the concept of a state. So now that's actually defined more generally for a C-star algebra. What is a state, or the states on A consists of all omega A to C, obviously continuous, which are positive, so fulfill this for all A and A, and are normalized. So omega 1 is 1. By the way, just as a side remark, I assume, just for simplicity, all the C-star algebras I mentioned to be unital. Okay, and then what is important is there are two reasonable or important topologies on S of A. One is the norm topology. So just you take S of A, it is in A prime, the continuous dual, and obviously this is a normed space, and you just restrict the norm to this, S of A, and then you get the restricted norm topology. And then you have the weak star topology. That is the coarsest topology on actually A star, such that EA, that's the evaluation map from A prime to C, omega is mapped to omega A, is continuous for all A in A. Okay. Now by Banach-Alaoglu, one knows or concludes that S of A is a compact topological space. And by Krein-Middleman, one can conclude that S of A is the closed convex hull of its extremal points, namely the pure states. Yeah. Pardon?
It's compact in the Weak start.
In the weak star topology, that's important. Not in the norm top, but in the weak star. That's yeah. So let me just write down. Yeah, and here star of A. These are the pure states. So these are the extremal points of S W star of A. Now, yeah, what we have been looking at, because gapped faces are more or less a homotopy theoretic problem. And I want to very briefly outline that. And to address that, we started looking into the pure state space here, both in the weak star and the norm topology, and tried to figure out the homotopy theory of those. Okay, but before I come to this, let me just make a remark on this here, and the one which I briefly announced, because almost exactly 100 years ago, Werner Heisenberg went in June 1925 to the German island of Helgoland and for escaping from hay fever, and he created a matrix model for quantum mechanics. And in a certain sense, that's what we are all doing, yeah. And then when he came back on July 9th, he gave his draft, so he found it very crazy. He gave that to Max Born, and Max Born has learned linear algebra, or at that time called matrix theory, from his study at the University of Wrocław. Born then looked at this and together with his student at that time, Pascual Jordan, they reformulated Heisenberg's square gadget, so to speak, in infinite matrix form, and so to speak, matrix mechanics was born. And in a certain sense, what we have here in all these co-limits and so on of matrix algebras, that's, I mean, a cook-up, so to speak, of this original matrix mechanics. So this conference is timed well because it's exactly 100 years after matrix mechanics was invented. Yeah, so that's just as a side remark. Okay, now let me come to gapped faces. So assume you have an irreducible representation. So here H can be, obviously is infinite dimensional in general. And you look at the Hamiltonian H, and you assume it's gapped. So what does that mean? That means the spectrum of H lies in the following set. Lambda 0, that's a real value, plus epsilon to infinity, where epsilon is larger than 0. And we assume the kernel of this is 1, yeah? So it is a one-dimensional. And what is a gapped face? So what you then say is the eigenstate, just take a normalized eigenstate, call this V0, and V0, V1 are said in same phase if there is a path HT of such gapped Hamiltonians with the ground states Vt connecting V0 and V1. Okay. So this, in other words, shows clearly that one wants to look at is at pi 0 of something, yeah? So gapped faces in the space-time dimension d plus 1 are pi 0 of some kd. And Kitaev's conjecture mentioned many times. Yeah.
Can you define a gap Hamiltonian without introducing representation?
That is a very good question, and I cannot answer it because actually I would like to answer it, and it's a question we have asked ourselves. I think this is a very crucial point. Yeah, I mean, what you can do, and I think it was in Bruno Nachtigall's talk, is that you can define what a ground state is independently of a representation, because you have a time evolution, and then you can write that as omega a star delta a larger or equal than 0. But gapped, I am not sure.
So you insist on just a single lowest energy state. If there's symmetry, that might be.
Okay, I mean, right now here, this is more motivational, obviously, and I swept that a little bit under the rug. You probably have additional conditions on the HT you allow. Let's say finite range, or where the interaction comes from a certain space, like in Bruno's talk, or in the work of Anton Kapustin. And one also at some point might consider that maybe at some point there is the lowest eigenvalue has multiplicity too, but it depends on the situation. So this is not.
And just for the definition of gap, before we consider paths.
Pardon? Yeah.
For the definition of gap or paths.
Yeah.
You insisted that the.
Yeah. Yes. I insisted. Yes, that's right. But obviously there are other possibilities, and it really, to my understanding, it's not yet known if you change this, what comes out.
Okay.
Yeah. Okay.
So what's the connection? Like you have H, but is H connected to A in any way? I mean, you start with it saying, you're just representing.
Yeah. Okay. I mean, okay. So maybe I should have written here H0. Yeah. So that's the H0 has ground state V0 and H1 ground state V1, and you have this path. But let me point out, this is really at the center of the problem, yeah, that a uniform mathematical definition has not been given, and one needs to find them, one. Okay, but Kitaev's conjecture mentioned many times, that is that KD is homotopy equivalent to omega KD plus 1. Okay, so now let me come to the state spaces again, let me here. And the first thing is P of A in norm topology. And in this first paper we wrote on continuous K-Disen and GNS construction, we developed that, and actually these are old results more or less, but the Pn, it decomposes in open connected components and then these are the superselection sectors. P omega of A, where omega from A to C is pure. So what does that mean? P n of A, N stands for norm topology, has many connected components, and actually, as pointed out in the very nice book by Peter, Peter Nikens, these are uncountably many, yeah, in general. So, and each of these connected components, what is that? So rho is in p omega of A if and only if pi omega and pi rho are unitarily equivalent. Yeah, and these are exactly the superselection sectors defined by physicists, by algebraic quantum theory. And Daniel has given a nice overview talk, which can be found online on that. Okay, and now each of these sectors actually can be determined how it looks like. So each the omega of A is biholomorphic equivalent to the projective Hilbert space P of H. And there actually exists a canonical map from P of H to this, which is given in our paper. And this guy here carries an infinite dimensional Kähler manifold structure. So the Hermitian metric is given by, you have the sphere in here, and by making this a Riemannian submersion, you get the Hermitian metric on P of H. And now, because we are interested in the topology, so P omega of A, which is biholomorphic to PA, is a K Z2. Yeah, so its homotopy theory is known. Okay, it has non-trivial homotopy in degree 2, that's isomorphic to Z, and all the rest is 0. Yeah. Yeah. Yeah.
Statement. So Pn decomposes in open sets, and each open set is represented by a pure state.
Each open, yes, I mean, you take a, yes, so this is an equivalence class of pure states, yeah? And two pure states are in there in the same superselection sector if and only if the corresponding G and S representations are unitarily equivalent. Does that, then you had a...
Is it the holomorphic structure on P omega of A?
Yes. Well, I can write you down the map, actually. Let me just see. So you have a map R, P of H to P omega, and it maps R. So that's a vector in the Hilbert space. You take array, and this is and you apply it to an element of the C-star algebra, and that's equal to psi pi of A psi. Okay. Psi is a unit vector, A is an A, and this is actually this is a homeomorphism, and you just turn it into a biholomorphic. You endow this guy with a holomorphic structure that this becomes biholomorphic, and it does not depend on the choice of, actually you have P omega, yeah? So it is a canonical holomorphic structure. Okay. Yeah.
Does depend on A be UHF?
What?
Does A have to be UHF for this result?
Well,
UHF.
it has to be UHF, I think, if you look at how many there are. I mean, uncountably many connected components, but this is not dependent on UHF. Yeah, so these results here, this decay into connected components being this superset has nothing to do with the UHF.
Ability just any C-star algebra?
Yes, actually, it does not even depend on commutativity or non-commutativity. Yeah. Okay. let me just continue with the weak star case. And there, the situation is very different. And it's the following. So if A is simple and separable, one knows by work of many, mostly Eilers, but also it goes back to some work by Kitaev and Arens and others. One knows that P of A, let me just write the star, is path connected and locally path connected. Okay. And it's actually even metrizable. Okay. So that's actually very different to the norm case, because in the weak star topology for all, I mean, our quantum system or quasi-local algebras, they are obviously simple and separable. So the pure state space there is connected. It's even path connected. And each sector, the omega of A, is dense in P W star of A. This follows from a result by Kishimoto, Osawa, and Sakai. Yeah, this is completely, I mean, impressive that each of those sectors is dense. And now it's even, I don't want to say worse, but it's even more surprising. Namely, in this first paper of the Boulder group here, we proved pi 1 of PW star of A is trivial, you know? So it's simply connected, you know? And the method, how we proved that was, I mean, if you have a loop, you disentangle it step by step and use this Kishimoto, Osawa, Sakai result recursively and repeatedly. And then later on, in a result by Daniel Spiegel and myself, we showed that pi k of A is 0 for k in n if A is UHF. So here you need, coming back to your question, here you really need UHF algebra. So for all quantum spin systems, I made a mistake here. I need the PW star of A. Yeah, so the homotopy theory of the pure state space of an UHF algebra in the weak star topology is trivial. Okay, so that is, in a certain sense, disappointing, but maybe also encouraging for interesting work. Yeah.
Daniel talked about this result before. I thought you could weaken like up to like for the simple separable nuclear real rank 0 or something.
Yes, we have a more general result, and I will come to this. So it is real rank 0, non-elementary, simple. I have to look up, but anyway, I come to that in a minute. Okay. Anyway, so then the question arises: is that a uniform picture that the homotopy theory of pure state spaces always in the weak star topology is trivial? And it's not. And actually, but then a further questions arise: is it, let's say, deformation invariant or Morita invariant? So what kind of type of invariance is the homotopy theory of the pure state space? And to show you how widely it behaves, let me just look at the commutative case. So if A I come to your question in a second. If A is a commutative C-star algebra, the pure state space is isomorphic to the character space, meaning to the spectrum. Yeah, and then, so A commutative, and then P star of A, that's the spectrum of A, and by Gelfand duality, this X can be any topological space, yeah? So just take an arbitrary topological, I mean, not topological, compact topological space, take the algebra of continuous functions on it, then its spectrum is X. So you get any homotopy type you want, yeah? So there it's just completely different. So then the next question arises, I mean, I mentioned deformation invariance, and I mentioned Morita invariance. Okay, now let's look at the non-commutative torus. So that's my old hobby of deformation quantization. And so these are C-star algebras A theta, where theta is an R. And how are they defined? So generated by U and V, so by two operators, and with commutation relation UV is equal to e to the minus 2 pi I theta VU. Okay? And what has been shown, for example, by Mark Riefel, who has written a couple of very nice papers on this, this is a so-called strict deformation quantization of the torus. Yeah, the torus is a symplectic manifold. I don't want to go into these details, but now let's look at P W star of A theta. Okay, let's look at first at theta is 0. So then we get back to the torus, and obviously we know by Gelfand duality coming here what then the homotopy groups are. So pi k of A0, pi A0 is Z2 for k is 1 and 0 else. Okay, and now then that's case 1. The next case is theta irrational. So these are, from the point of view of non-commutative geometry, really interesting cases. Then A theta is unital, simple, separable, and has real rank 0. So, and then the result by Daniel and myself shows pi k of P of A theta is 0 in all degree. Yeah. So for all irrational ones, irrational angles, that is has 0. Is weakly contractible. But now what's absolutely surprising, at least I think, let's say theta is P over Q, is rational, no common divisor, Q larger or equal than 2, just some technical things, and then pi k of P of A theta, now it's actually a longer list, is 0 in degree 0, Z2 in degree 1, so that's like the torus, but then it deviates, so it's Z in degree 2, 0 between 2 and 2q minus 1, Z for k is 2q minus 1, and now higher homotopy groups of odd-dimensional spheres come in for k larger equal to 2q q minus 1. And that's crazy. At least I think it's a little bit crazy because you look as this is unbelievable, but it is obviously not deformation invariant, yeah, because it jumps crazily back and forth. But it is like it is. So we
Buffered space type thing, or I mean, how
can you.
is there some like way you can think about this classically, or is there not? Is there any sort of
I have to admit, we were very surprised about this, but we have, and we to prove this, we used actually strong results by Dons Hoffman, so where they identify the C-star algebra with a certain fiber bundle or sections of a fiber bundle with values in some matrix algebra, and then the primitive ideal space, and that you can identify, and there you have these spheres appearing, and then you can compute it. Yeah. Okay. So
Did Michael Hermele take a look at this, and
I have to ask him actually. Yeah.
how will he interpret this as a physicist?
That's a, well, I can ask already here the physicist, but I will ask. This is a good idea. I will ask Mike what he thinks about this. Yeah, and but okay. So, and another homotopy theoretic result that's actually in the first paper.
Look at this and conclude that the norm topology is the one we should focus on and the weak start.
That is actually a very good question, and I had at other conferences discussions about this, and here obviously too. I personally don't think the norm topology is very helpful, because if you look at the commutative case, for example, the pure state space in the norm topology gives just a discrete topological space. Each character is then 1 point. So it is crazy. Either one, things get strange. Yeah.
It's not as strong compact open topology.
That is yes. There are other topologies, and that might be actually, so to speak, the way out. Yeah. But both the norm and weak star topologies do not have optimal properties. But from the point of view of physics, the weak star topology is more natural because it's the weakest topology such that all transition probabilities are preserved. So that is a little, I mean, it's not a proof, but it's an indication that it's a little bit better than the...
Sometimes when you build families of the mechanical systems, the compact open topology is more natural.
Yes, I agree, and maybe we should look at that. Yeah, so that's right. Yeah. Okay. So next thing I want to look at is a certain fiber bundle. Again, I come back now to the norm topology, and let me call it a principal fiber bundle. So now we look at A should be unit UHF, yeah? And we look at the following map, which maps the unitaries in A to EU of A is U times omega of A is omega U star A U, where A is in A. So I should write this like this. And omega is pure state. Yeah, so this is a pure state given, and then if you let the unitary group act on this sector via this, you get a map. And our result, I just write Boulder group for those is P U of A to the omega of A is a principal fiber bundle. And let me just be very precise in norm topology. Okay, so and what is the structure group? Is U omega of A that consists of all U in U of A fixing omega. Yeah, that's, so to speak, the fixed point group here. And this group, actually both groups, U of A and U omega of A are both Banach-Lie groups. And U omega of A acts from the right on U of A. So this gives you the right action of the structure group. And what you need is, maybe I write here, locally trivial. That's the key thing. And this local triviality, to prove that, you need a continuous version of Cadison's transitivity theorem. So the continuous version of Cadison's transitivity theorem was proved by Daniel Spiegel in his PhD thesis, and we have it also in this paper. But using that, you can show that this is really locally trivial. In other words, that it has local sections, yeah? Local sections by continuous Cadison transitivity. Yeah, so, okay, now then another question arises, well, is that bundle trivial or not? Yeah, and it is not. And that is, second theorem, also Boulder group. P U of A, the omega of A is not trivial. And how do we prove that? Actually, it is also a somewhat surprising proof. So we started with UHF algebras, and a UHF algebra, they are in bijective correspondence via Klim's famous results with supernatural numbers. So these are sequences of Ni, where Ni is a natural number or infinity. Okay.
How big is the structure group of this bundle? Like, is that typically finite dimensional, or is that a huge impact?
It's infinite dimensional to my, I mean, I have to think about this a bit more, but my immediate answer would, but with some caution, yeah. Actually, I think it's infinite dimensional, because what you can do, you can write down the Lie algebra. Because it's a Banach-Lie group, you have, so I think it should be, but I need to figure out details, but that's my guess. Okay, and so the supernatural numbers are such families, and in principle, what can you think about these are, actually, you can think about this number as being something like this. So the pi are the prime numbers ordered in increasing order. And then this supernatural number is this infinite product of the pi to the ni. I mean, that's just a symbolic representation of what that is. But what is very interesting is that each additive subgroup Q of Q can be represented as some Q of n, where n is supernatural. I can write that down in detail, but it's a little bit technical, so I just skip that and refer to our paper. But the point is, I repeat, every abelian additive, so with respect to plus on Q, subgroup of Q can be written as in the form Q of n, where n is a characterizing supernatural number. It's not uniquely determined, but you can also say if you have n and n prime different, when is Qn equal to Qn prime, yeah? But what is needed, and I'll write that maybe here on the right, is that one can compute now this U of H, the homotopy groups of U of, so I k U of A is now 0 for k even, and is this group Q of delta A for k odd, where k, that's the supernatural number characterizing A. So there is an isomorph, the supernatural number characterizes A up to isomorphism, yeah, according to Klim. And then pi k of U omega of A, that is slightly different, is 0 for k even, so that's the same, C cross Q of delta A for k is 1, and Q of delta A for k larger than 1 and odd. Okay, and simply because in degree k, this is not the same like this, and the base space, this guy here, is simply connected, the bundle cannot be trivial. Yeah, so that's a very easy, straightforward homotopy theoretic conclusion if you have these homotopy groups. Let me just make a remark about originality. So that stuff is original, so we haven't seen this anywhere else. Actually, we haven't seen this computed anywhere else, but there exists an old result by Schröder, who computed the homotopy groups of the general linear group of an UHF algebra. And obviously, because these are homotopy equivalent to U of H, the same stuff comes out. Yeah, so one could have used their result. Okay, so now let me come in the last 15 or 17 minutes back to Kitaev's conjecture, and erase this here. So, Kitaev's conjecture. So as has been mentioned several times, what is a spectrum? That's in particular in Mike Hopkins' talk, spectra were explained in detail. So this is a sequence of pointed topological spaces with weak equivalences. So actually this is a loop spectrum. Has weak equivalences YD with omega YD plus 1. And what one can associate to it is a generalized cohomology theory. By associating to each topological space Y upper D of X are the homotopy groups of X to YD. So these are the homotopy classes of maps from X to YD. it fulfills all Eilenberg Steenrod axioms besides the dimension axiom. So it's a generalized cohomology theory. And by Brown representability, you can go back. Yeah, I mean, if you have a generalized cohomology theory, you can get a loop spectrum out of it. And there are many examples. I mean, topological K-theory, there's an algebraic K-theory spectrum, cobordism theory, Eilenberg-MacLane spectra, and so on. So, and Kitaev, he conjectured there is a loop spectrum which we call K, K0, K1, such that K I0 of KD are phases in space-time dimension D plus 1. Okay? So, and again, all over the lattice X. So, and Z to the power D. And in this collaboration with the Boulder group, our first approach to
You need some contractible phases, the gap, invertible gap phase, something like that.
yeah, that's yes. So of gapped invertible phases. Yes, you're right. I should have. Yeah. So that's okay. And one idea, obviously, by Brown representability is try to create parametric phases. Construct parametric phases. And then by Brown representability, construct K. Yeah. This we haven't succeeded in doing this in all detail, but at least it's still an approach, and hopefully on the long run, this will work out. But we had in our Homotopy Foundations paper an approach where using so-called E-infinity spaces to at least construct a loop spectrum. Yeah, and that's, I want to briefly now explain. Okay, and how does it go? And so what we first do is we have a particular topologically enriched functor, which is covariant, and it's called P gamma. It goes from finite dimensional Hilbert spaces with their tensor product to compactly generated topological spaces. And how does it work? So we have here this category, and then we go via A gamma to the category of C star algebras. That's exactly the stuff I wrote down in the beginning. A gamma of H, where H is a finite dimensional Hilbert space. That was, so to speak, this infinite tensor product of the B of H's at each yeah. Okay, and this is the C star algebras. They are unital and nuclear, and they have a tensor product because they are nuclear. And then you take the state space, and then you restrict to B gamma, and you go to the pure state spaces. And actually, it is a little tricky. I come to your question in a second. It's a little tricky to define this as a functor in the sense what happens on morphisms. First, let me remark that the morphisms in here isometric embeddings. So it's really the category of finite dimensional Hilbert spaces, and they need to preserve the Hilbert space structure, meaning they are isometric. Yeah.
I think the people who at the other location can't see the board if you rock.
Oh, yeah. Thank you very much. I appreciate it. So I actually was advised before that I shouldn't do that, but so I hope that's now visible. Okay, and in addition to this, there is we have monoidal structures in here, obviously the tensor product, and also in here, which is just the Cartesian product. And so what we have too is plus natural transformation eta between P gamma of H1 plus P gamma H2. And let me just write that vertically, P gamma H1 tensor H2. Okay? And this becomes a lax monoidal natural transformation. Okay. Now, and what this is the prototype of what we call a quantum state type. So we call this actually, is called universal quantum state type. Okay, and what is a general quantum state type? That is a functor Q gamma from the same categories to compactly generated topological spaces. And I'll just write this to abbreviate this a little bit. It's meaning it's a subfunctor of this maybe this is not an optimal notation of this universal quantum state type. What does that mean? Q gamma of H sits in P gamma of H. So this consists of pure states on A gamma of H and contains all completely factorized states. And what else? Yeah, likewise on the morphisms, it's the restriction of the universal quantum state type and restricts or is restriction on morphisms and with respect to eta. Yeah, so there's also a lax monoidal functor transformation, which is the restriction of this. Okay, so we have, we call this now eta Q gamma. Okay, and now in the last couple of minutes, let me just explain what we did. Giving such a quantum state type, we construct two important spaces. Construct U gamma, this one, of H. Again, H is a finite dimensional Hilbert space, and this is the disjoint union of I large equal than 0, Q gamma of H tensor I, and Q gamma of H tensor infinity. This is the colimit of I tensor psi, Q gamma of H tensor I. Okay, and now what is a result we proved? It's again Boulder group. This guy here is an E infinity space. By time reasons, I cannot go into the details of the definition of what an E infinity space is, but very briefly, it's a homotopy associate and commutative H space, which all higher homotopies also being properly encoded. And what is very interesting is that under certain conditions, this is the Y0 of a spectrum. Yeah. So, and it's in particular an infinite loop space. And so you can get out of this a spectrum. And let me just add the final thing. If Q gamma of H is invertible, then what does that mean? That pi 0 of Q gamma H tensor infinity is a group. Then Q gamma of H tensor infinity is an H group. And an infinite loop space defining a spectrum. Okay, I have been a little bit short on really explaining the details why this guy we think is a good candidate for classifying those gapped invertible faces. Yeah, but we have in this homotopy foundations paper, we explained that in a bit more detail. What is missing, so to speak, is the jump from one dimension to a higher one. Yeah, so this, I erased it already, but it has been written up many times. KD is homotopy equivalent to omega KD plus 1. Yeah, so something like this is missing. Then these spectra here are connective, which we, and then the Kitaev spectrum would be not connected, and so the connective, and so there are a couple of subtleties which we still need to address, but we are hopeful. Okay, thank you very much.